So for number one on this, the first thing we need to do is what? What's the first thing we need to do with all of these? du. So the degrees of unsaturation is equal to what here? It's equal to 7. I'm counting on you to be able to calculate that. And it's C8H5NO2. When you see a degrees of unsaturation above 4, ding, 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 benzene ring. All right, so this is telling me, most likely, not always, benzene ring. And the benzene ring counts for how many degrees of unsaturation? 4. So this is for 4. So how many do I have left to go? So I still need to get 3 more pi bonds or rings. All right, 3 more pi bonds or rings. All right. IR, what does the IR tell us? The IR we have peak at 32, to 28. And it says it's broad. What does that tell you? OH. Right? Tells you OH. 22, 32. We're not sure. Is that an OH for carboxylic acid or an OH for just an OH? Do we know? Not yet, probably, right? We don't know yet. 22, 32. What is that going to be? What could that be? It could be a nitrile, or what else could it be? Or C triple bond C, right? We're not sure. Right? We don't know. The IR doesn't eliminate those possibilities. It gives us options. What about 1703? What does 1703 tell us? What kind of stretch is that for? What functional group? C double bond O. What about 1250? What does 1250 tell us? I think CN single bond or CO single bond. Okay, still not narrowing it down, but okay, it's there. So that's what we get from the IR. The best way to do these problems is one part at a time. Trying to do this all in totality is too hard. Focus on one part at a time. Do the degrees on saturation, write down what you know from that. Do the IR part, write down what you know from that. All right, so we know that from IR. Good. Now the NMR. So from NMR, I like to label these out. So they have, how many peaks do we have? 3. So that would tell me this molecule is probably pretty, for a molecule that's C8H5NO2, that's pretty what? Probably is pretty symmetric, right? There's some symmetry involved with this probably. So the NMR we have a peak at 13.6. That's 1H and a singlet. What is that? What's in 13.6? Where's that? What do you think that's going to be? A carboxylic acid, right? That's way, way de-shielded. So we're going to say that is this piece. And if I label this as HA, that's what this would be, right? Do we know what's bonded over here? No. So we have our first piece for sure, right? And that takes away how many degrees of unsaturation does a carboxylic acid take? 1. So now we're down to, so we did -1. Now we're down to 2 up here, right? Let's subtract the carboxylic acid part away from our molecular formula. So minus here, C, how many H's? 1H and 2 O's, right? So what do we have left? C7, H4, N, right? H4, like I said, H4, right? Good. Let's go to the next peaks. The next peaks we have are 8.11, worth 2 H's, a doublet, and 7.995, 2 H's, and a doublet. So presumably, if we label these B and C, they have to be what? Next to each other, right? They have to, if they're going to be coupled, there's only one other thing they can be coupled to, is each other. Now, what region are those peaks in? Benzene region. Now, this is where it gets, how many, so if I draw a benzene ring, which we've been expecting, there's 6 spots on the benzene ring. How many H's are going to have to be on this benzene ring? So according to this, there's 2 and 2. That's 4 total, right? So how am I going to substitute the benzene ring to get 2 types? So how many different substituents am I going to have in this benzene ring? 2, right? So it's going to be a di-substituted benzene ring. The question is, right, so we know it's di-substituted. I'm going to put 1 here. Where should I put the other substituent? Should I put it here, here, or here? So opposite. Why opposite? That's right. Because then if I draw these H's in, if this was H, these are both C's, and these could be both B's, right? And presumably whatever's here is going to be different than whatever's here, right? So that means these two will be the same, these two will be the same, and are they going to couple to each other? And how will they be coupled? As what? How many nearest neighbors does C have? 1, 2, 3. Right? So 1, 3 bonds away, so that'd be a doublet. So that makes sense, right? Do you need to know which one's A and which one's B and which one's C specifically? No. You don't need to know which one's which specifically. So there's a whole piece. Let's subtract that piece out. So what's that worth? Minus C6H4. Yes? We got a C and an N left. Well, we're still short, what, 2 degrees of unsaturation? So which do we make? And we know we have a nitrile or an alkyne. So what do you think we got? Probably a nitrile. That's all we have left. So now the trick is, so now we have 3 pieces, right? I have the carboxylic acid piece, I have the benzene ring piece, and the nitrile piece. There's only one way these can go together. Right? You put, right, this has, if you end up with 3 pieces, and one of the pieces has 2 open spots, right? The other 2 pieces have to go on that. Now it might matter where they go. Sometimes it might matter about frequencies and stuff, but in this case, does it matter? Does it matter if I put the nitrile here or here? Not in this case. Right? So the final answer then, is that di-substituted benzene ring, the carboxylic acid O, which is A, B, which could be here, and C, which could be this H and that H. So that's the final answer. What we'd like to see on the problems is working it out just like this. Right? Work it out just like this. Write down things that you know. Right? Write down things that you know. Right? Help yourself. Give yourself as much information as possible. All right, taking a look at from our workshop, number 5. This is the second problem for Unit 2 from workshop number 5. It has molecular formula of C10H12O. Degrees on saturation for that will be equal to 5. So that should be telling us we have a benzene ring, which counts for 4, so we still need 1 more left to go. If we get our IR, what does the IR tell us? We have peaks at 3024. That should tell us probably sp2 hybridized CHs. A peak at 2936 should tell us sp3 CHs. Peaks at 1609 and then 964. This should tell us CC stretches. And 964 is a very specific one found on table 13.5, and that's for a trans alkene. So that would be telling us this. The IR tells us that. Okay, so we got a lot of information from the IR. If we have an alkene, which we do, according to the IR, that would cover our last degree of unsaturation, right? That's okay. Got that checked off. Let's scrunch that down. So the IR tells us a lot of information. The NMR is going to tell us a lot of stuff as well. NMR says 7.21 we have 2 H's. That's a doublet, and it has a J value of 8 hertz. We have another peak at 6.80 worth 2 H's. That's a doublet that has a J value of 8 hertz. We have another peak at 6.29 worth 1 H. That is a D of Q, a doublet of quartets. And that J value is equal to 15 and 5, so it has 2. So it means it's coupled to 2 different things. 6.07. We have 1 H. That is just a doublet. And that J is equal to 15 hertz. 3.729 worth 3 H's, and that's a singlet. 1.824, that's worth 3 H's, that's a doublet, and the J, the coupling constant for that is 5 hertz. Okay. At this point, I like to label A, B, C, D, E, and F. So I like to start with the top one. So if I look at these two, I should see these and say, well, these are both in the aromatic region. It looks like we have 2 different types and 4 total. So that makes me think of an aromatic ring that's di-substituted in this manner. So it has H's, right? These could be H A, and these could be HB. I don't know what's at the top. So now for my molecular formula, which is C10H12O, I'm going to subtract C6H4, C4H8O, so that I can check off A and B. I knew I had to have an alkene, right, for my IR as well. I knew it had to be trans, so I know I have this, and that matches with the vanillic region from around 6.0, 6.5. So one of these would be C, and one would be D. So I can check those two off, subtract that piece. So minus C2H2. I got C2H6 left over, and the oxygen. I look at one at 3.79. That's pretty de-shielded. That makes me think, right, a CH3, and it's a singlet. So that makes me think of a methyl group. This may be next to an oxygen, so that'd be one piece. So that'd be for E. Check that off. Now F is 3 H's and it's a doublet, so it has to be near something. And I look at these coupling constants. So I said, well, who else has a coupling constant of 5? Well, C has a coupling constant of 5, so I should put F should be close to C, I think. Alright, so maybe I'll put that even right there. I'll say, hey, this is HF, because it needs to be 3 bonds away from C to be coupled, so I think that's where HF is at. So now I have all my pieces. I just need to put it together. I essentially have 1, 2, 3 pieces, so there's only one way for this to go together and for it to work. So the final would be aromatic ring with the O, CH3, the alkene that is trans. Alright, so I draw my H's in. H's up top that were coupled to C. These would be F. That makes sense, the 3 bonds away. This would be C, because C is both coupling to F and it's coupling to D. right? So C has two different coupling partners, hence the doublet of quartets. D is turning C into a doublet. F is turning C into a quartet, so it's a doublet of quartets. The other one's in the ring. It's not imperative that you know which one's which. You just know they're both there. All right, one's A and one's B. Put in the last one. And what does that need to be? That needs to be E. That's the one that's de-shielded next to the oxygen with no nearest neighbors. So the first thing you're going to need to do is what? What's the first thing we do with all these problems? Degrees of unsaturation. In this case, the du is equal to what? 5. So that should tell us what? What are we thinking? Benzene ring. So we're thinking benzene ring. Because a benzene ring has 4 degrees of unsaturation, which would leave how many left over for us to need? 1. So literally write this on there in here. Hey, remember, I need 1. Right? Write that on your test. We'll have plenty of scratch here for you. What's the next thing you want to do? Let's look at the IR stretches. So we have a stretch at 30, 28, and what does that mean? 30, 28. If it doesn't say broad, it's not an OH or an NH. So what would this be? A CH. What kind of CH? A CH stretch for a sp2 hybridized CH. Not necessarily an alkene. Not necessarily an alkene, because it could be a benzene sp2CH, right? So it's just an sp2 hybridized CH. We have another stretch at, what, 29, 26? What would that be? A CH. What kind of CH? sp3CH. sp3 hybridized CH. We have another one at 17, 17. What is that going to be? C-double bond O. We don't know what type, but it's a C-double bond O. Would that cover our last degree of unsaturation? Is that a pi bond? Yes. So we can check that off. Right there, right? Check it off. Well, good. I'm going to go with all my degrees of unsaturation. Benzene ring has 4, right? 3 pi bonds in a ring. And then the carbonyl. We don't know what kind of carbonyl it is yet. So now what I like to do, I like to draw the molecular formula over here and say it's C10H12O, right? You did the math, you can find the degrees of unsaturation. So what I like to do is subtract out pieces now. So I know for sure I have what? I have well, I know for sure, let's just wait for the benzene for a second. I know I have a carbonyl, right? A CO. So one of my pieces has to be this. Squiggly lines represent I don't know what's on the other side, right? So I can subtract a CO from my molecular formula. So I can say minus a carbon and an oxygen. So I do this to keep track so I don't lose a carbon or forget a hydrogen. All right? C9H12 is left over. Right, see that? So I have one piece. All right, I have a carbonyl as one of my pieces. And I don't know what's on either side yet. Whatever. So far, so good? Now let's look at the HNMR. The HNMR, it says we have a range from 7.41 to 6.99 ppm, and that is worth 5 hydrogens, and it's a multiplet, an M. So I'm going to call this, I guess I'm going to call it A. Now multiplets mean it's too messy, maybe things didn't get resolved. So remember how we did something with our 45 megahertz NMR, and then we did something with a 300 megahertz NMR? Remember we saw that sometimes with the 45 it's not fully resolved, right? So you expect maybe to see 3 peaks, but maybe you just see one big glob, right? So high def versus low def. Right? So that's what this is kind of saying here. A multiplet means that you couldn't see the peaks you'd expect to see. But it is telling us some information about the benzene ring, because let's think about this range. At 7.41 to 6.99, what kind of hydrogens are in that range? Look at your tables. What range is that for? Benzene. And now how many H's are there? How many benzene H's do we have? 5. So how many different things are on our benzene ring? How many substituents? One. Do we see that? This would be a mono-substituted benzene ring. So we know just from this, we know we have this, and I don't know what's there, right? So that's an H, an H, H. And I don't need to know, right? In reality, if you were asked to pick how many hydrogens normally you'd have, you would probably say 1, 2, and 3, right? But these hydrogens just are too similar and they're not resolving, right? We don't have enough high definition for this. So we just call it a multiplet and give it a range. So now we need to subtract what from our molecular formula? H5 and then 6 carbons. So now we have what? We have C3H7. Good? So now we have 3 other peaks left, right? So we start out with 4. So the other peaks we have left are 2.87, and that is worth 2 H's, and it's a triplet. We have a peak at 2.75, that's worth 2 H's, it's a triplet. And then we have a peak at 2.11, that's worth 3 H's, and is a singlet. So the one at 3 H's, let's do that one. Right? I like to usually go de-shielded to shielded or shielded. I usually box it in. Right? So the most shielded one is 2.11. So what's that going to be? It's a CH. It's worth 3 H's. It's going to be probably a methyl group, a CH3. Well, yeah. And how many neighbors does this methyl group have? So, right. What kind of notes can we write to ourselves? So there's a CH3. So if I said B, C, D. So these are D's. So we know that this is at 2.11. We know it has, write a note to myself, no neighbors. Because what's going to happen is we're making all these pieces, and when we try to put them all together, we got to remember some hints. Right? So one of our hints for this one is no neighbors. Right? No nearest neighbors. What about the frequency? It's at 2.11. What range is that? So it's a little downfield than normal. So but look at your table. What could it be next to? Right next to an oxygen? If it's right next to if it's bonded to an oxygen, it would be probably around 3.5. Next to a carbon double bond to an oxygen. Maybe next to a carbonyl. So maybe up here we'd say, well, maybe this makes sense that D is up here next to that piece. Right? Because at 2.11 that would match. Does it have any neighbors if it's up there? Nope. So I would say, I would check that off. So we still need to subtract a C and 3 H's though, right? So we have C2H4 left. So it looks like we have A covered, we just got D covered. So now we're left with B and C. So B and C are both triplets. So what do you know? Are they coupled to each other? They have to be. Right, there's only 2 things left. They have to be coupled to each other. So that means they need to be right next to each other. Right? So that piece would look like what? If I drew a CH and a CH, that'd be next to another CH2, right? Do we know what's on the other sides over here? No. So let's say this one's B, this one's C. So now you have that checked off. Each would have 2 nearest neighbors, so they'd both be triplets. Both work for 2 H's. Now we have, what do we have left? We have left now, how many pieces? We have 1 piece, 2 pieces, 3 pieces. Now you got to figure out a way to put these together and then go back and double check. So there's essentially 2 ways. Actually, no, there's only 1 way you can put this together. Right? If you have 3 pieces left, and one of those pieces has 2 ends, and the other ones each have 1, you can't mess it up. Right? So what's the final structure going to look like?
The benzene ring connected to the C2H2 or H4 side, and then that's connected to the other one.
Has to be this. This will be your final structure. Tricky parts, one of the tricky parts was 2.11, recognizing that needed to be next to the carbonyl. But you also recognize it had no neighbors too. So you knew it couldn't be near anything else. Also kind of tricky, right? So 2.87 and 2.75, technically that's outside your allylic range, isn't it? The allylic range is from 1.5 to 2.5. But those are just approximations, so it's not always perfect. Right? So they're a little bit outside the range that you would expect, but they're not so far out that it's unreasonable, right?
Can we talk about how we got the hybridization from the IR?
Sure. So if you look at your IR table, the top of, what's the top, 13.5? The top of 13.5, it says different types of CHs, right? It says SP2, SP3, and SP. SP CHs are around 3,300 and are sharp. SP2 are from 31 to 3,200 and are sharp. And then SP3 are always below, right? Always below 2,900. So the top of that right there, yep. Top of 13.5, there's your numbers. That tells you the top of 13.5 tells you the type of CHs. And I told you if it doesn't say it's broad, then it's not an OH or an NH.